Welcome back. In this chapter, it's all about creating recipes and layers. We create our custom image recipe, machine definition, and distribution. We then add applications of different technologies and build systems, trying to cover several use cases. So let's get started. Bitbake provides us with the Bitbake-layers tool to create layers and do other operations on layers. Let's look at the usage. You have several subcommands. The add layer adds the layer that you pass to it as to your bblayers.conf file. So previously we added the meta-OE layer manually, but you can use this tool. You can also remove a layer from your bblayers.conf with the remove layer command. The flatten command takes all of the layers that you currently have into a configuration and outputs them all into a single layer, basically flattening out the metadata that you have. So show layers shows the currently configured layers. Show recipes lists all of the recipes from all of the layers that you're currently using. And the tool that we will be using to create a layer, the subcommand is the create layer. We can go through some of these commands as an example. So for instance, Bitbake-layers show layers. So this shows the layers that are currently active in our configuration. Bitbake show recipes is also layers show recipes is also quite useful. For instance, if we want to, it supports patterns. So if we want to list all of the images, we can use this, for instance, this pattern. Okay, so this lists all of the recipes which match that pattern. So let's go ahead and create a new layer. Let's go to our sources folder, where we located all of our layers. We will create a layer called meta-hubshuffle. See what the contents are. Actually, I have to use my host machine for that. Let's go ahead now and create our own image recipe. Bitbake actually has a recipe tool which is useful for creating recipes, but in our case this recipe will be very simple. It will be a single bb file, so we can just create it by hand. So I'm going to create a directory called recipes core. Inside this directory I will create another directory which normally would be the recipe, would have the name of the recipe. In this case it's just an image. And I will create the image which I will name example image. Now we won't be creating an image from scratch. We will actually be basing it off the core image base, just like the Raspberry Pi images are created. So we're going to base this image on core image base, and for this I will require or import. So what this does is basically include the file, and the file is the core image base file. We can actually use the Bitbake layers to see if the Bitbake is parsing the recipe correctly. In this case, see if it shows up. We could obviously just create the image, issue the command to create it. Okay, so we got a... Okay, so it failed to include... There's a typo in that. Let me just fix it. Recipes for So as we can see, it's including the recipe correctly, so we can just go ahead and try and build it. So Bitbake's execution has terminated and it has created the image successfully. You can go ahead and flash the image if you want. As you can see, the image artifacts were generated and they're located in the same folder as they were previously. So we can go ahead now and customize our image. Remember that in local.conf we had added i2ctools and Vim. Now this is, we can actually add this to the image, which makes more sense because we can then version the image and share it. Because this local.conf file is temporary. So I'm just going to go ahead and delete that file, that line, and then I'm going to edit the image definition. So let's go ahead and add the i2ctools. Vim. Now you could add this on the same line. It's a matter of preference. Okay, there we go. We can rebuild the image. And it should have the same, exactly the same behavior as if we had defined the image install variable in local.conf. We can also do other customizations. For instance, we can define a compatible machine regular expression. So what this will do is that it will limit the machines for with which this image is compatible with, and the machine name has to start with Raspberry Pi. So only allow for machines which start with RPi. And the documentation for this is actually in the manual, as we can see. I'm going to repeat the step of flashing the image so you guys can see. It's the example image. The wrong directory. We can actually use the symlink. We'll next create our own machine definition. In order to create a machine definition, we have to create a folder named machine inside the conf folder in our layers directory. We will be extending the Raspberry Pi 3 machine, so I'm actually going to copy that file so we can override the variables defined for that machine. We will name it Raspberry Pi 3 Custom. So we can start customizing some of these fields. Custom machine. one variable we have to define is the machine overrides, which allows us to override any definition, any variables for that for the Raspberry Pi machine. I have the Yocto manual open here. So this value allows us to override, if we specify the Raspberry Pi 3, the variables defined for the Raspberry Pi 3. So machine overrides, oops. Guess we can leave this the same. Now in the machine we can, since this will be interpreted by the Raspberry Pi 3 meta-layer machine code, we can actually add the meta Raspberry Pi customization variables to this file. So we can go ahead and remove what we had added to our local.conf. Go to the build folder, local.conf, so we can remove these and add them over here. So we can enable UART, enable I2C. You can actually go ahead and add other things. If you look at the Meta Raspberry Pi 3 documentation, you'll find descriptions for them there. SPI bus. Now, since we won't be using the GPU for this specific image, we can reduce the amount of memory dedicated to it to the minimum, which is 16 if you look at the documentation. And disable the splash screen. And the boot logo also. This is all in the manual. So there's another thing that we can do, which is to auto-load specific kernel modules. So if you remember, I had to manually load the I2C dev module. So we can add that here, so it's loaded during boot. Okay, there we go. We just defined our own machine. But we need to actually specify it in our conf file. Custom. So we can go ahead now and build the image. So while building the image, it actually exited with an error code, and it said that it couldn't locate the BSP definition, and no def config was specified for the kernel. And what this generally means is that the kernel recipe was badly configured, and actually it was a typo in our custom machine definition. So I had written machine override instead of machine overrides. So after fixing that, the recipe succeeded. The process of creating a new distribution is specified at 3.19 in the Yocto development manual, and they do recommend that you create a separate layer for your distribution, but in our case, just in order to keep a single layer, we'll just create it inside our meta-hubshuffle layer. So you just need to create a distribution configuration file in the conf/distro directory of your layer, and you need to specify the variables that are present here. So let's go ahead and create the distro layer and create a configuration file for our distro, which we will name just example distro. Let's go ahead and edit it. So we can specify the maintainer. include the email. Now we will base our distribution on Pokey, so we have to require that file. I specify the distro name, the distro and the distro name. The version, code name, the SDK in case we're going to generate one. This is going to be like a suffix. So there we go. So as a last step, we need to edit our local.conf in our build folder to use our definition, our distribution. So now we just need to rebuild the image. Okay, it seems I made a mistake. Probably left the quote. Yep. So what type of things can we customize in a distro? Well, one of them is the host name. As specified in 5.2.5, in order to change the host name, which by default is the same as the machine name, you have to either create a recipe that appends to the base file's recipe, or you can include the following in a configuration file, which we'll do for the distribution file. So let's just copy this and insert it in our distribution configuration file. Okay, so I'll just put bblayers.conf. So now if you rebuild the image, you should see in the prompt that host name. So if you boot your image now, you should see the bblayers.conf in the prompt. And obviously the host name is set to bblayers.conf. If you don't want to look at the archives of the images, you can find the images, the raw rootfs files in the work folder. So it's work, and then the image name -pokey-linux, and here it's in the example image, so it's the image recipe and rootfs version and then rootfs. So we can actually also look at the host name file. In this case, it's the old machine, so it's... So what other tweaks can we do at the distribution level? A big change is changing the init system, which we will do now. Let me just comment this. So at the moment we're using sysvinit, which is a quite classic initialization system, and a more modern system is systemd. So we will replace it now. So we will add it to distro features, the recipe, the systemd recipe. We'll set the virtual runtime initialization manager, and this is in the manual obviously. And we actually have to remove sysvinit so it's not built. So in order to do that, you use the remove suffix, and we're going to add to that sysvinit. You can also add the initialization scripts, which which are templates. So these get included in the rootfs. As they're called units in the systemd. And we also have to blacklist the sysv init from the features. So I'm going to rebuild the image and we'll see systemd booting now. So I've just booted up the system, and as we can see, systemd is being used. Let's just verify that with systemctl. Status. There we go. So cool, we got systemd replacing sysv init. Now say for instance you want to decrease the image size, or you want to actually remove features from the distro or from any other, from the image install variable for instance. What you can do in that case is use the bitbake command, which is -e, which basically dumps the environment variables for a given target or recipe. And in our case, imagine that you want to look at the distro features. So you can use this pattern here, which Bitbake will basically dump the variables for the example image recipe, and then we're grabbing for a line that starts with distro features. So once the command executes, we can see which features are being baked in our distribution, which are quite a few of them. Now I've gone ahead and disabled some of the features, which we can see here. For instance, Bluetooth, support for X2 file system, infrared, PCM SIA, which is like an old laptop peripheral interface, and many other variables. And the rootfs size actually back down from 44, so this is before, if you don't disable those features, to 39, so we actually saved 5 megabytes. That's just one way of using this, of exploring the values of the variables and then changing them and seeing how things affect the resulting image. As a last change to our distribution, let's configure the default time zone. So in order to do that, we have to actually install the tz data package in the image. Now, if you actually look at the folder for this package, which is something we can find with the Bitbake-layers show recipe. Show recipes actually. So it's in the meta layer, which is part of Pokey. And now I actually have to grab for it. So if we look at this recipe, we find that this package actually has sub-packages. And we get a hint at that by this provides runtime. So in my case, since I'm in London, London, I have to specify tz data-Europe also, besides specifying the tz data package. So image install and tz data. So we added that entry to the image definition, and now in the distribution we can actually set the default time zone. Going to rebuild the image. So the Raspberry Pi is just booted, and just to confirm that we have the correct time zone, just gonna cut it. There we go. So in order to change the root password, I just searched online and ended up in the Yocto wiki, which suggests two ways of doing it. One of them is in the image recipe, so we just need to insert a code which looks like this. And you can also do it in a config file. You would just have to use a different syntax. You can also add other users. So let's go ahead and use that in our image file. Now, in order to generate the password, we can do it with OpenSSH, as I'll show. So for instance, to set the password to Tor, I would use this command. Just copy paste the hash. Set it to the root user, so that's the command syntax. We have to be careful and escape the $sign characters. Generate the image. As an additional example, we can install Network Manager on our image. In order to do that, the first thing we should check is if the recipe already exists in our layers. So we can do that with Bitbake-layers show recipes. So as we can see, none of the layers that we are using at the moment include that recipe. What we can do is go to the Open Embedded Layer index and search for the recipe. So you would go to Recipes, Network Manager. Choose one of the recipes. In this case, I'm going to choose the latest version. And here we have some details of this recipe. The packages it includes, the dependencies, and so on, and the package config options, which we'll discuss shortly. So let's go and inspect the layer that includes this recipe. So as we can see, this layer depends on Open Embedded Core, which we already have, and additionally MetaPython and meta-OE. So let's look at our bblayers file. So we already have meta-OE. Let's actually inspect the Open Embedded Layer folder. So as we can see, the layer that we want is already checked out in our source folder. So let's go ahead and edit our bblayers to add that layer. We can now go ahead and repeat the command, see if the recipe is already present. Now we do get this confusing error. Something that can help you is just using Bitbake to try and bake our image, or in this case Network Manager. And this error message actually does help us, because it says that the networking layer depends on the meta-Python layer, which is also present in the Open Embedded folder. Okay, so we just need to add that one. Let's repeat the show recipes command. Okay, so it found the recipe and we should be ready to go and include it. So let's go ahead and include Network Manager in our image. Network Manager. Now there are additional packages that are present in this recipe, and how we know that is looking at the recipe itself. So if we actually look at the source code of the recipe, and if you're familiar with Network Manager, you know there's a tool called nm2e, which is a command line tool that uses n cursors, which is quite useful. Now this recipe has this packages variable which defines the packages that the recipe provides. So in our case, we have additionally the nm2e package, so we can add that package as we will soon. Now, as another example, this package inherits from the bash completion recipe, which we can look at the source for. And this one is in meta, it is actually in Pokey. Meta classes, and it's called bash completion. So that layer, that recipe rather, includes this class, and what this class does is also append to the packages variable a package which is named after the recipe which includes it, or the package that includes it, and it has this suffix bash completion. And what this is, as the name suggests, is provide bash completions for that recipe. So what we can do is, besides installing the Network Manager core package, is install Network Manager nm2e and Network Manager bash completions. Completion. Okay, so let's go ahead and bake our recipe and verify if Network Manager is working. Okay, so I did a typo. I'm gonna correct that. Manager bash completion. Actually, I'm going to separate this into separate lines. This one. So I've just booted up our Raspberry Pi, and just to make sure that Network Manager is actually working, we can enter nm2e. so we can see it's working. Let's also check the system service status. It's actually camel case. Just a few exceptions. One of the few exceptions. So it's loaded and enabled, as we can see here. Now, we do have at the moment systemd installed with networkd and resolved, but we will be taking care of that in the future once we customize a recipe for systemd. Now, before we advance to application recipes, let's just do some final tweaks in our image recipe. So what we can do is remove old images once a new image is built. This has already been done by I think it's meta-Raspberry Pi, but you get to know it anyway. We can also limit the image fs type generated. At the moment I think we have x3 and tars, so we can just limit it to RPI SD image if we want. So we produce the RPI image format. And this will remove all builds. Also, I don't think, we still have the splash screen enabled, so if you want to disable that, and this is also in the Raspberry Pi documentation, the meta-Raspberry Pi layer. So we can go ahead and disable that. Image features remove. Oops. You can also do something quirky, such as printing a message. For instance, in do.fs for the do.fs task. So we do this by appending to the task. And as you know, you can list the tasks for a given recipe with the command to list the tasks. So it would be this one of the last tasks. And we'll be using a warning message, just because the other messages of lower priority don't appear unless you're issuing a bitbake with the debug level on. So an image has been freshly built. And if you want to know the available logging facilities, you generally for these things it's a core functionality, so you can look at the core code, which is from Pokey. So meta classes, it should be one of these, logging maybe. Yes, we have bb-plane, note, warning, error, fatal, and so on. Now, other things that they also mention in the meta-Raspberry Pi manual is that we should include the wireless firmwares, which are, I think they are binary blobs from Broadcom. Now, I haven't found this to be necessary for some reason because the Wi-Fi is working, but we'll just add it anyway. Bluetooth. can we do? We can also install an SSH server. So this is an image feature. Dropbear, which is a lightweight SSH daemon. Now if you want to check what our image has at the moment, we can just expose all of the environment variables and grep for it. So we'll grep for something that starts with the image features. So I made a typo here. It's actually image features, image feature. Okay, so there we go. Drop there. Maybe the kernel modules. Yeah, those aren't being installed, so we can install those. Now I'm keeping everything on separate lines, but you don't have to do that. You can just include packages on the same line. Okay, let's rebuild the image and then test the SSH server. So the Raspberry Pi has booted, and as you can see, the quirky image, the quirky message showed up. And in order to test the SSH server, we have to make sure that we have an active connection to a host or to a network which has an DHCP daemon. In our case, I'm running a DHCP daemon with DNS mask in my computer, and I'm just going to try and SSH into it. Now the syntax that I'm using here is SSH pass, so I don't have to input the password. And then just a normal SSH client with strict host checking off, and basically so I don't get the entries in my known host file. So there you go, I'm in. Cool. One thing worth noticing is that the image size has increased substantially, and I think it's because we included all of the kernel modules. As we can check out, where did I have the image? It's here. No, it's actually here. There we go. So yeah, now our image is like an order of magnitude larger. We can also notice that although we specified in the rootfs types to only build our RPI-SDI images, we also have the X3 and tar BZ images, which I guess are dependencies in order to build a UBFS image. Now, just to investigate what exactly is creating such a huge file system, we can investigate the file system itself and search for which directories are occupying the biggest space. So we can see that lib alone is occupying around 400 megabytes, so we can go into that directory, repeat the same command. So firmware is the big culprit here. We sort this numerically. So this one is 17. Okay, say for instance that we don't need this component, which we probably don't. there's a very useful tool which is OE package data util, which allows you to, given the path, discover which recipe produced that file. So in this case, it's liquid.io, and the file name. So Linux firmware liquid.io is producing that file. So I guess the main culprit was actually Linux firmware. I did try Linux install remove, but that didn't do it. So I guess the solution is just to remove Linux firmware. And if you need the other firmwares, just specify it explicitly, like we are for the Broadcom chipsets. And that should bring the image down quite a bit, the image size. Okay, that is it for this. So next we're going to start creating recipes, application recipes. In this section, we'll be creating our first software application recipe. So I'm under the meta-hubshuffle layer directory, and I'm going to create a new directory named recipes-apps. Inside this directory, I'm going to create another directory for our first application, which I'm going to call Hello World CPP sources. Now I'm naming it sources because we're actually going to include the source file in the recipe sources, which we shouldn't by convention. It should only contain metadata, but this is just an example. So the first thing we should do is create the recipe file, CPP sources, which has a base name, and then underscore, and then the version of the software component, which in this case is just 1.00 as an example. Now, the next thing we should think of is where are we going to locate the sources? And for this, I'm actually going to open the development manual. Under section 3, creating recipes, the syntax we use to specify source files is this syntax over here. So source underscore URI, and we use file : //. Now, when we use this syntax, the build system fetches the files from the local machine, and the path is relative to whatever value this variable has. And inside the path to which this variable points to, Bitbake searches for the files in a specific order, which is under folders named after the base package name. And the base package name, this is the version without any suffixes. And optionally also a directory named just files. So in our case, I'm just going to create a directory named after the base package name. Now inside this directory, I'm going to create the source file. It's going to be a very simple C++ application. Going to make sure it compiles. Okay, that's fine, it's just missing the linker. Now another file that we need to create, which is obligatory, is the license file. And for this I'm just going to search for an example license file for MIT, for instance. So Pokey actually includes examples for license files, and you can find them under this directory. So it's Pokey/meta-files common licenses. And in our case, let's just choose MIT, for instance. So I'll be actually copying that content. So I'm just going to copy it directly. So recipes apps. And then I'm gonna copy it to a file named copying. So we go back to our environment. Now we actually define the contents of the recipe. So there are some fields that we have to fill. So there's a summary, which I don't think is actually needed, but makes sense. Sources. Then we have to specify the name of the license file, or the name of the license, sorry. So, and then we have to specify the checksum for the license file, just to make sure that no one tampers with it. So the license file is named copying, and we will be using an MD5 checksum. So we'll just grab that. Pasting it. I believe that's it. Then we have to specify the source files. So the syntax that we use is file : / and we have to specify both files, so the license file and the source file, which in this case is just a single file. Now we have to specify the location of the sources, which is in the current directory. And then Bitbake will use the files path. So now we're going to specify the do compile, since we don't have, this project doesn't use any Makefile or any build system Makefile. So we have to specify it manually. Flags. Name it after the base name. Go flags. That should be it. Now we have to also specify the do install task implementation. So we're gonna install it in the bin, user bin. And for that, as we saw in the previous chapter, it's bin there. And finally install the actual file. So this creates the directory. So each package has their own workspace, and you have to. So this isn't the sysroot, so you have to always create the directory beforehand at least once. Okay, so let's test out the recipe. Just need to issue Bitbake and the recipe base name. So in order to actually include this in our image, we have to edit the image file. So I'm going to edit it here. Recipe score. And then I'm going to add it at the end. The sources version. So as usual, image install, package base name, sources. So let's bake a new image and flash it in the Raspberry Pi. Oops, I forgot I'm not in the Yocto environment. Sometimes it's tricky when you're using Docker. Yes, example recipe. Example image, sorry. Okay, as you can see, I got the name wrong. So it's hello world CPP sources. Not CPP sources, hello world. CPP. Let's repeat that experiment. Okay, so that was successful. So now I'm just gonna flash the image on the Raspberry Pi and see if the binary is present. So the target is booting up. Okay, so there we go. In this session, we will be producing a recipe that's similar to the previous recipe, but in this case, we're going to use a Makefile instead of specifying the doCompile task. I'm also going to show the workflow that I generally use in order to enter the Yocto development environment. So the first thing to do is to actually enter the Yocto environment. I'm going to execute the start script. Now I got this error. You probably won't get it, but I've got it because I logged in this window manager session using another user. So using the original user, I have to activate the access to the X11 permissions, and now I should be able to execute this command. There we go. So in this terminal session, we are inside the Yocto development environment. I can actually go to the workspace and source the pokey OE init script in the RPI build directory. Now generally I use another terminal in order to explore the files. I do have them mounted so I can use the file explorer, but in this case I'm just gonna use the terminal. Okay, so in this terminal session I'm in the Yocto environment, and in this one I'm not, just to clarify things. So I'm in the recipes apps folder and our meta-hubshuffle layer, and now the first step is to create the recipe directory. I'm going to call it hello world cpp makefile. Next, let's create our sources, including the makefile. In this case, I'm going to use the files directory. I'm going to create the makefile. We're going to borrow the source of the C++ CPP, the main.cpp. And also the copying file. Okay. I'm just going to customize the source content so it prints a different message, just so we know when we run it in the target. It's fine. Now I'm going to create the makefile. Okay, so let's create the makefile contents. I'm going to assign a variable for the application name, which will be the same as the binary name. Compilation flags. Oops. Linker flags. then the LinkedIn libraries, which are probably only going to be the C++ libraries. So this is similar to the do install in our previous application. Now I'm going to create this variable dest dir, which recipe tool will then look at, and it will guess that is equivalent to the D, capital D variable, and it will actually replace this variable. Seems kind of magic, but that's how it works. Create a clean. So DevTool will actually use these targets, or the install one and the make, just make to build everything. Okay. Just gonna test it out, see if it works in this current environment. Don't have to do that, obviously. So it seems fine, make clean. Okay. Oops. So the next step is actually to create an archive of the sources. So I'm just gonna create an archive and name it, what am I gonna name it? Hello world, cpp Makefile, and then add everything. Okay. I'm going to remove the source files. Actually, I don't actually need to do that. I think I could just use recipe tool directly. So I was doing this outside of the Yocto environment, and obviously we can't do that because we can't use Bitbake. So I'm just going to enter the environment. Okay. Go to the workspace, sources. Recipes, apps, Makefile, and then I'm gonna invoke a recipe tool to create the recipe for us. So I was trying to invoke recipe tool, but the command's not found, which is expected since I haven't sourced the OE init script. So I'll do that now. To the RPI build folder. Now I can go to the sources. Again, meta-hubshuffle, recipes, apps, Makefile recipe. So let's see what options recipe tool gives us. Okay, so we will be using the create subcommand. So let's see what options we have for that. So you have various options here. You can, such as providing a -m, or the machine that the recipe is compatible with, the name version which we will be using. So recipe tool, create -n, hello world, cpp Makefile, and then the version 1.0, and then we are going to use the -s to point it. Oh, sorry. Actually, it's just the sources where it can find the source files. So it's going to be in files, and then the archive. So let's have recipe tool do its thing. Okay, so recipe tool created a recipe for us. Actually, I spelled it wrong. It's fine, I can just rename it. Now let's see what recipe tool did. Okay, so it did find the license. So it created the checksum and the license variables for us. Source URI is filled. Do config is fine because we don't need to do anything. It's running the make, and as we can see here, it's actually replacing the dest dir variable with our own. Okay, seems fine. Let's give it a try and actually try and build it. So bitbake, hello world, that's it. Okay, base name. Let's try it out. Okay, so we got a build error, and it seems it can't find the license because it points to an invalid file. Now, in these situations is where a dev shell actually comes in handy. So to invoke dev shell, we just issue bitbake and the recipe, and then for the command we just specify dev shell, and that should open a terminal instance within the build environment of this package, so we can debug what's going on. Okay, so dev shell opened up. Okay, so it is actually in an empty directory, and if you go level up, this is the directory it should be in. What this tells us is that the s variable isn't being set correctly, and we can fix that by going into the recipe and actually changing that to the work directory. So let's try that out. Okay, let's try and issue the command again. Let's try and rebuild it, or build it either. Okay, it seems like it was successful. Let's actually look at the rootfs to see if the binary is there. So let's go to Yocto, the workspace, and then the build folder. So tmp work, and then in our case it's the Raspberry Pi machine, the custom machine, and the example image, version, rootfs, user bin, and hello world. There we go. So it's present there. So if you want to, you can try and flash the image now, and the application should be available. Okay, so in this section we learned how to use recipe tool and dev shell to debug when something goes on. Also, don't forget that if you want to actually install this in the target image, you have to add it to the image recipe. So for that we have to go to recipe score, and I've already actually added it. So we just append the recipe to the image install variable. So next up, we'll create a recipe that's a bit different. We will use a Git repository as the source of the application, and it will be a Python app using Flask, which is a web framework. And additionally, we will specify a systemd service unit that we will install in the target, and will execute the app during the system boot, so that we can then visit the app endpoint through the web browser. So let's get started. So as usual, we will create a directory for the application, which I'm going to name just Python Flask Hello World. I have created a Git repository that we can use, which is at github.com/hubshuffle/python-flask-hello-world. So we will be using recipe tool and the create subcommand. So in this case we have to specify the name, which I'll name after the project name, which is Flask. No, it's Python Flask Hello World. Version 1.00. And now for the source URL, I'm going to use the Git repository source URL, the HTTPS URL, because in this case you don't need the SSH host keys to be installed. I'm just going to copy paste that, give it to recipe tool, and see what it creates. Okay, Okay. So let's inspect the contents that recipe tool created for the recipe. So since the project doesn't have any license or copying file, it just defined the license has been closed, which is fine for this case. Source URI seems correct. Package version, source revision, the source directory. No, it's not doing anything for the compilation tasks, which we will change shortly. Let's just try and use this application with Bitbake to see if it's working correctly. If the recipe is correctly defined. Okay, it seems fine. Now, what this application will do specifically is the equivalent of the Flask Hello World application, which is basically just define an endpoint that you can then visit through the browser, and it just returns the text, the string hello world. So for I'm going to define a systemd unit. So we're going to create another source file that we will append to the recipe. So I'm going to name it Flask Hello World .service. I'm just going to define a simple systemd service. Python. So it will always restart in case it crashes. Restart sec. Now, if you're not familiar with systemd units, that's fine. You don't need to. Standard error says log. Now this is the important bit. It will execute the /user/bin Python Flask, which is the artifact that we will have to install in the rootfs. .py. And the service will start once the multi-user environment has been set up. Target. So now we will have to customize the recipe. Now the Python file is actually named app.py. So we can customize the install first. Okay, I'm going to use a tab. Python script. So once again, this creates the directory where we will install the Python script. Additionally, we will install the service. Now this is in the systemd unit there. So this is also defined in the bitbake.conf that you can find in the pokey/meta/conf folder. Okay. I forgot one thing, which is /system. And normally the service files have these permissions. Actually, I forgot the app here. App.py. We're gonna actually change the name. What was it? Python Flask. Which is what we defined in the service file. No, we haven't. Oh, yes. So we're going to install this file. Okay. Now for the files that Bitbake will actually use to install in the rootfs, we have to specify the files variable, which can be found here in the reference manual. It basically just specifies the files that will be included in the resulting package. So let's go ahead and define that. And the service file. Service. Now we also need to specify the systemd service file, which is also in the reference manual, so that Bitbake knows where to install, what service to include for systemd. So that the service is enabled. And actually, in order to use this, we have to inherit the systemd class in our recipe. Just going to remove these. No, we're not going to need this, and the decompile also we can get rid of. So inherit systemd. So let's issue the build command, see if the recipe is valid or if it's being executed correctly. Okay, so we got an error. Okay, so it seems like it can't find this file. Let me just make sure that it's correct. Oh, okay, so we have to move that file. I'll just... Let's try that again. Okay, so it couldn't find the file, and it's probably because I forgot to add it to the source URI. Yep. So we obviously need to add that here. So it's just // service. Okay, let's try it once again.
Okay, it seems okay. Let's just make sure it's present in the rootfs. So file, API build, tmp work. Okay. The example image, rootfs. Let's look at the system, the service file first. Python. Now, obviously it's not present because I didn't actually add the file either to the image install or to the recipe, and I haven't actually built the recipe, so that's normal. So let's go ahead and edit the recipe so it installs this file, this package, sorry. Button. Okay, now let's build the image again. Okay, so it's doing the rootfs, installing all of the packages. I'll be back once this is done. So the image has finished building, and now we can actually verify if the files are installed correctly. So I'm gonna see if the service file is installed. Okay, seems fine. And the script user bin. Python Flask hello world. You actually see if that's correct. User bin. Okay, seems fine. So I'm gonna flash this image, and I'll be back so we can test it. And just so we go through the flashing process once again. API build, TMP deploy images, and then we sort of have the SD card plugged in through a USB dongle. Just gonna DD it. There you go. Stage progress seems fine. Okay, see you soon. Okay, so the system has just booted up, and I'm gonna check the status of the service. Ask hello world. So it seems there's an issue because the service is being restarted and there was an exit code. So I'm going to stop the service. And I'm going to try and execute the script directly. Okay, so the problem here is that Python isn't actually installed because we forgot something in the recipe, which is to specify a dependency that the recipe has on Python. So let's go ahead and edit the recipe. Now this is a runtime dependency, and for that we have the rdepends variable, which we are going to specify now. So Python 3, and there's also another module which this depends on, which is Python 3, the Flask module. And the syntax for that is Python 3 dash and then the package name, which you would find through pip, the Python package manager. So Python Flask. So I'm going to rebuild the image, and we will retry the process again. So see you soon.
So after reflashing and booting the target again, let's check the service status this time. So this time the service is running, and through the debug messages we can see that it's listening on port 5000. I have the Raspberry Pi in the same network as my computer, so we can try and visit this endpoint. Okay, so it's working correctly. So in this session we are going to learn how to create a patch for the Python Flask Hello World app, and we're going to use dev shell for that, just because it's easier. It makes the process easier because it puts you inside the work directory. You could do this outside of the Yocto environment if you wanted to. So in terms of the changes that we're going to make, we're just going to change the port of Flask. And in order to do that, we just need to assign a different port number. Let's say we want that number. So we are going to use git to create the patch. So I'm just going to do the commit, change port to 7777. And we're going to use git format patch to create the patch. So we're going to create a patch based on the commit that we just did. So one commit behind is going to be the reference for the diff. Okay, so let's look at the patch contents. So I'm going to copy this patch to our recipe folder. And I'm going to exit dev shell. So we have the patch. I'm going to move it into the files directory. And now it's time to edit the recipe so that we include the patch. So using patches with Bitbake is quite easy. You just need to include the patch to the source URI. I forgot the name. And that should be it. So let's actually build the image again. So now I'm just going to verify the contents of the rootfs to verify if the patch was applied successfully. Example image. Okay, seems fine. So there you go, that's how you use patches in Bitbake. Now, one type of recipe that we haven't created yet is a recipe that appends to an existing recipe. And in this case, we will do so with Network Manager. And what the recipe will do is just append a network configuration so that once you flash the image, you have a functional network configuration. For instance, your Wi-Fi access point, the configuration for your Wi-Fi access point is already present in the rootfs, and you don't have to configure it manually. Now, Network Manager has the network configuration stored in etc Network Manager System Connections, in the System Connections folder, and in this case it's empty because I haven't created any network configurations, but I'll do so using nm2e, and this is running on the Raspberry Pi. You could do so in your host system. It would be the same if you use Network Manager. Now I'm going to activate a connection which is to my Wi-Fi access point. So I have to specify the password. So I've gone ahead and used nm2e to create the network connection file. You could do it by hand. So what I'm going to do now is basically just copy paste this content into a recipe that we're going to create. So let's go ahead and actually create the recipe directory. Meta-hubshuffle. I'm going to create this recipe under a directory called recipes-connectivity or networking. And I'm going to create a recipe which appends to, actually I have to create that directory first. So this will append to the network manager recipe. In order to, you have to actually know the recipe name, so in this case I'll just show it with Bitbake-layers, show recipes, since I already know the name, since we added it in a previous section. Okay, so that's the recipe name. So network manager, now I have to create a file that is named, that has the same name as that recipe. And then comes the version, which in this case we don't care about the version, so we're just going to use a wildcard. So it appends, this will be a recipe which will append to every version. And then instead of .bb, it's .bb append. Okay, so in this case we have several variables that we have to define for a bb append. One of them is the file's extra paths. Prepend. So this prepends whatever we define to the file paths of the original recipe, and in this case it will be this dir, which is the current directory, /files, and that's it. Which so we're going to use a files directory. We also have to add to the file that we will be using to the source URI as usual. And in this case, I'm going to name it, what was it? Home Wi-Fi .nm connection. And then customize the or append to the install task. So what we're going to do here is basically just copy the file to the etc. To the corresponding directory. File. And I know the file permissions by just looking at the file permissions that Network Manager uses. And this is actually important because otherwise Network Manager won't actually use the file if it has different permissions. I'm going to install it in the sysconf dir network manager, which is basically this directory, system connections. Okay, I'm gonna add ending white space. Now we have to copy the configuration file under the files directory. I'm just going to paste the content. Okay, and going to try and build the recipe, which Bitbake Network Manager. Okay, so it seems like I actually got a parsing error. When the errors are this big, it normally means that the recipe isn't well formed. And it actually gives us a hint. So, an expected end of file. Let's take a look at the recipe. And sure enough, I forgot the quote at the end. And actually, this should also be quoted. Okay, let's go ahead and try that again. So the recipe build was successful, and I've also gone ahead and rebuilt the image, so the rootfs gets populated with the network configuration file. And I'm actually just going to check if the file is present. Okay, so next we can either reflash the image or actually use the package manager to install the network manager again. So I've gone ahead and rebuilt the package index and installed network manager on the using open package, and sure enough the configuration file is present. So by now you're probably tired of having to build and reflash an image each time you add or modify a recipe and want to install it in the image. The answer to this is using packages. We mentioned package feeds in chapter 3. This is one of the final steps Bitbake executes when producing an image. Depending on the package_classes variable defined in a configuration file, Bitbake generates the corresponding package formats, which can be RPM, deb, or IPK files. If we take a look at this package diagram in the Yocto reference manual, we can visualize this better. In build/tmp/deploy folder, the package groups are created for each target architecture, including the specific machines, for instance in our case the Raspberry Pi _custom machine that we defined. So package groups are built for each one of these. We can expose these package feed groups and use them as repositories that the target can then source to install packages. An alternative is to manually copy the packages to the target and then install it, but that becomes tiresome, especially when dealing with package dependencies. So the basis for getting package management is to have an HTTP file server in our host machine and configure the package manager in the target to use this address as a repository. So let's configure this so we can use packages instead of reflashing the image each time. So we will go ahead and edit the variables that are necessary to support package management in our distribution layer configuration file. So we're going to set a bunch of variables here. Configure package management. So we're going to add that to the image features. We're going to add IPK. I chose to use IPK in this case. So we're gonna, by default, only the RPM packages are built, I believe. So package_IPK. Don't forget when we use append, which the difference between the append and this operator is that append creates the variable if it doesn't exist, while this one just appends to it, and if the variable name actually doesn't exist, it doesn't do anything. So in this case we have to specify a space character here because it actually performs string concatenation. Okay, so, and we also want to install the open package OPKG manager in the image. So we're gonna also use the append operator. We're also going to enable prserve, as we mentioned in the previous video. So prserve, what it actually does is each time a checksum for a task changes, it increments the packet revision. So in this case, to enable it, we have to use this. I just saw this in the documentation. Now, in order for OPKG, it has a configuration file in etc /opkg/basepackages.conf, and it basically specifies the repositories, the default repositories. So I'm going to set defaults here. Now, this is the IP address of my local machine. In your case, it's probably different, because later on we will install an HTTP server, which in this case will listen in the port 8080. We'll get to that later. Base paths will be empty. Now, in terms of the arcs that we're going to expose, which are correspondent to these, we do have the Raspberry Pi arch, which is a specific one. But I've seen that, for instance, the applications that we include, that we built ourselves, the recipes are not included in that, and they're only included in the architecture, which is named the Cortex, which is a more generalized case than our specialized machine. So I'm only going to expose the packages that exist in here. And by the way, if you don't see this folder yet, that's normal. It's because we will build the package index, and obviously those packages are only built once you add this IPK to the package classes. So I'm gonna append this architecture, and that should be it. The next step is to rebuild everything. And this will take some time, because Bitbake will basically, if you didn't use IPKs before, it will generate IPKs for each package. In this case, I've already run it, so it didn't actually do anything. So after that, you have to perform the command bitbake update package index. So this creates a package index, which is what is it called? It's a tar file. So what package index does is basically build these files. So now that I've built the image and I've already flashed it, you can go ahead and do that also. What we have to do next is go to this folder where we are at the moment, which is in /tmp/deploy/ipk, and we have to start an HTTP server here. I have Python running on my machine, so I'll be using that to start an HTTP server. And when I say in my machine, it's not inside the Docker instance, because the network configuration for Docker makes it difficult to access the Docker instance from outside. So we'll just skip that and use the host machine. So I'm going to go to RPI build, tmp deploy IPK, and I'm using a Python module called HTTP here, which is also known as simple HTTP server. You can use whatever HTTP server you want. I've gone ahead and installed that using pip. So it's already installed. And to start the server, you just need to perform the command HTTP here, and then --host, and you specify it with a null IP address, so it's accessible from all network interfaces, and then the port, which is 8080 in this case. I've also already booted the Raspberry Pi with a new image, so if you look at the etc open package and base feeds, you can see that our repository is already configured here. So this was populated by the changes that we made in the distribution. And if we want to, we have to update the package index. So this gets the package index from our machine. And then you have several commands. One of them is list, to list the packages. So we can search. So we can search for the Hello World packages. I'm probably just going to do a list and grep. And so the packages that we created manually are present here, and if you want to install them, you can just go ahead and do a pkg install and then the name of the package. In this case, it's already installed, so you can also remove it. So remove. So it's not present anymore. But let's go ahead and reinstall it, just for example's sake. Okay, there we go. We have package management configured and installed. In this chapter, we'll build a recipe that uses CMake. I have an example repository in github.com/hubshuffle/cmake-hello-world. So again, we're gonna use recipe tool. I'm in the recipe apps folder, so we're gonna create the directory for the this application. I'm gonna name it after the project, which is CMake hello world. I'm gonna use recipe tool create -n with the name CMake hello world -v for the version, and then the repository URL. I'm gonna use the HTTPS URL since we don't need the SSH keys if we use it. So I'm going to try Bitbake right away to see if it can build this package. Okay, so right off the bat we have an error, unknown target install. So if we look at the recipe, it doesn't have any install specific specialization for the recipe. And if we look at the CMake lists, it also doesn't have any install instructions. So in this case, we would either need to edit the CMake lists file or change the recipe file. So let's go ahead and edit the recipe and add an install specialization. The binary. Now the binary is named CMake-hello-world.cpp. So as usual, we create the directory. Appender. And this will be the CMake world. Install in the Appender also. Okay. And as we see, this recipe inherits from the CMake class, so it's able to understand CMake lists. Let's try that again. Okay, so there you go, it seems like it's successful. So adding support for CMake is straightforward also with the recipe tool. So let's go ahead and add this recipe to our images, to our image definition. Okay, there you go. You should be able to build the image or install the package. Seems I got the name wrong. It's just CMake Hello World. So I'm gonna edit this. Okay, so the image built successfully. Next, we will be looking at, in the next chapter, how to use, how to generate an SDK, and then how to use DevTool. So see you then.